I will continue the course of this morning. So in the morning we reduced the study of this kind of zeta function to the study of Dirichlet series of this form. So now I will explain how to study the meromorphic continuation, and if I have time also I will give some results about the values at non-positive integral of this kind of zeta function. So the first thing to do is to approximate this by integral like this Dirichlet integral. And first we need to prove analytic continuation of this kind of integral. And as I explained, we can use resolution of singularity in general case. But here, for a practical reason, I will restrict myself to the case of polynomial of positive coefficient and explain the method in this for this class, because for this class one can use Newton polydron, which is combinatorial object, and we can compute everything by hand in some sense. And for application, it is important to have explicit change of variable, etc. So we assume that P depends on all variables. So on X1 and on all variable. So the first thing, in order to study this, the meromorphic continuation of this integral, is to produce some change of variable. So we define the Newton polydron of P at infinity by E infinity of P. It's as the convex hull of the set of support of P minus R plus N. So if you write P of the form sum of alpha x alpha, so the support of P, it's the set of alpha such that alpha is different from 0. So it looks like, for example, for n equal 2, if you have the support will give you a finite number of points, and you take every point, do that. And then, for example, in this case, the Newton polydron, it's this set. And we are interested by extremal points of this. We define xp as the set of extremal point of the Newton polydron. For example, in this case, you have one extremal point here, one extremal point here, and one extremal point here. And for any alpha extremal point, for example, we have a cone here defined by this extremal point. By using this cone, we can exhibit the change of variable. So to be more concrete, I need some definition. So I write my polynomial px sum of alpha alpha x alpha. So x alpha, it's x1 alpha 1 xn alpha n, and we define the Newton polynomial in this way, and we define also if lambda 1, lambda n are a vector, linearly independent vector, of Rn, we define a map omega equal omega of lambda 1 lambda n in this way from 1 infinity to 1 infinity in this way. So to x equal x1 xn, we associate omega of x defined by x mu 1 x mu n, where mu 1, if you write mu I as a vector mu 1, mu I 1, etc., and if you write your vector lambda I as lambda I1, lambda En, then this is only the transpose. We have the link between the mu Eg and lambda, it's lambda Ge. So the matrix of the mu Eg is the transpose of the matrix of lambda Eg. So we define this map, and they will play an important role in the cycle. And we define omega n, the set of omega lambda 1 lambda n, such that lambda 1 lambda n are vector with integer coefficient and are linearly independent. So now I will give some property of these maps. They have some beautiful property. So if you write omega of lambda 1 lambda n, so the Jacobian of this map, it's easy to compute. It's equal to the determinant of the matrix lambda Eg times a monomial divided by x1 is n, where 1 is the vector 1, 1, 1. So this is a monomial times this is an integer. If you work with omega here, and this is a monomial. And we have also some other good property. So we have the fluent formula, omega x alpha. It's equal to x omega alpha. It's equal to x1 lambda 1 scalar products of lambda 1 and alpha, etc., until xn scalar products of lambda n alpha for any alpha. And another property is that if P is monomial, then P composed with omega is also monomial. And if P is a polynomial, then it's also polynomial. And also, if the third one is more important, is if P has a dominant monomial, x alpha, then P composed with omega has a dominant monomial, which is x omega alpha. Omega tilde, maybe I have to precise, it's omega tilde, it's the linear map with matrix lambda G. So with this notation, we can prove the following. Can prove for the following theorem. This theorem of Argos, and there are also some variants about by Deneuve and his collaborator. So if you are interested by the continuation, you have also Deneuve, etc. So let P1 we are in R x1 xn non-degenerate polynomial. So in this talk, I will take as a definition, because we are working in the quadrant, I will take as a definition of no degenerate. We will say that P, the polynomial P, defined in this form, is non-degenerate if P, if there exists two constant C prime positive, such that for any x in 1 infinity n, C P star x less than Px, but it's enough to suppose that there exists one C, because this one is trivial, where P star is equal the same polynomial, but you take the absolute value of the coefficient. So, for example, polynomial with positive coefficient satisfy this assumption. And this class, it's essentially the same class. It's just there are some connection here. Yeah, there are some connection between. But here, this is enough because we are working in the quadrant. So this is enough for. And in some sense, it's more simple to express. So for no, if you have R non-degenerate polynomial, then we can associate to Newton polydron of this polynomial at infinity a finite number of transform omega 1 omega m in this set of this form, such that one apps to a set of measure 0, the set 1 infinity n is the disjoint union of the sets omega k of 1 infinity n for k from 1 to m. And 2, if q is a polynomial of n variable such that it exists E from 1 to R, such that the Newton polydron of Q is equal to Newton polydron of Pi. So if Q is a polynomial with Newton polydron equal to one of these Newton polydron, then for any k from 1 to m, the polynomial Q composed with omega k has a dominant monomial. This is the main part. So why this theorem is interesting for us? So before giving an idea of the proof, I will explain how one can use this theorem to prove analytic continuation of the integral. So we start. So by using this theorem, we'll prove the following theorem. Let P and R plus x1, xn, which depend on all the variables. So there exists sigma some C positive such that the directly series converge absolutely in the half plane real S bigger than C. We denote by sigma A, its abscissa of absolute convergence. absolute convergence. And to the S, now I am dealing with the integral. This is dx, and can also add some monomial. So we can put here some monomial. Okay. And this integral has homomorphic continuation to the whole complex C, and the singularity with poles of order less than n, and the set of poles Sp, it's contained in a sequence of the form sigma e minus k over m0 k in n, where m0 is some integer we depend only on the Newton polyhedron of P. Yeah, I suppose that for simplicity, I set a polynomial with positive coefficients, so it is not dirichlet. Yeah, just for simplicity, I present in this. And we have also modulus growth. Has modulus growth, which means that in vertical state it's great at most polynomial in polynomial way. So how to prove this theorem by using this one? So you start with your polynomial now, and by using this theorem, we can write the set 1 plus infinity n as the union of omega k of 1 plus infinity apps to some set of measure 0. Okay? And so from this you deduce that your integral x eta dx, it's equal to the sum for t from 1 to m, t from 1 to m of the integral on the set of the image of the you deduce this formula by using this decomposition, and then you use your transform omega k to rewrite this in this form. Jacobian of omega k of e t y, and as I explained, this is a monomial because this function transforms monomial en monomial, and the Jacobian is also a monomial, and this new polynomial has now a dominant monomial. This is the difference. The polynomial, the first polynomial p has not necessarily a dominant monomial. But now we transform it to some polynomial with dominant monomial. So this reduced to, so it is enough to study the integral. It's enough to study the integral in the case where P has a dominant monomial. If you are able to study meromorphic continuation in the case where P has a dominant monomial, then by using this decomposition, you obtain in explicit way a meromorphic continuation of the general case. So now I will explain how to prove analytic continuation in the case where you have a dominant monomials so suppose now that P has a dominant monomials P x alpha. So we can write Px as E alpha x alpha plus sum of the other monomials P less than alpha x A beta x beta. So by using this, we have P minus x, it's equal to E alpha minus x minus S alpha, factor 1 plus some beta less than alpha, E beta x beta minus alpha. Yeah. What? An exponent? Yeah, please. Thank you. So now we return to the integral. So this is equal to E alpha minus S, the integral from 1 to infinity n, x eta and minus S alpha, and 1 plus sum of beta less than alpha, E beta, x beta minus alpha. And this is also equal to, by sample change of variable xi 1 over xi, this is equal to the integral from 0 to 1 of x minus S minus eta plus S alpha. And maybe for simplicity, I will use, just to simplify the notation, you put this here. Just for simplicity of transformation, I will write after minus 1. And here you have 1 plus sum of beta less than alpha, E beta, and x alpha minus beta minus S, and here you have dx. So as you can see, for this function, it's look like an inversible. So this is not dangerous factor. So this function look like the normal crossing case. So to conclude, have just to we define for epsilon positive small enough. So small enough, we define the Hankel contour E epsilon as the limit path in C minus R plus, defined in this way. You have here 0, or you have here 1. You've come from 1 plus E0 and until here, until epsilon, and you do that, and you return here to 1 minus E0. Yeah? This is Hankel path. And we consider the, we denote by log z the determination of the logarithm of the log in C minus R plus. And by using this, with this notation, we have the following lemma, which said that let f z1 zn be holomorphic function in a neighborhood of the set 0, 1, n, in a complex neighborhood of this real set, and in Cn, let lambda or vector of complex coordinates verifying lambda j positive for real lambda j positive for any g. So then for any small epsilon positive, we have the following formula: the integral from 0, 1 n of f of x lambda f de x1 xn dx1 over x1 dxn over xn, it's equal to 1 over the product from g from 1 to n of exponential of 2pi lambda j minus 1 times the integral on e epsilon n of z lambda f z1 zn dz1 over z1 dzn over zn. So this is a sample. It's not easy to, it's not difficult to prove. It's just a sample calculation. Do it variable by variable. And by using this formula, as you can see, this function, if you, this is our function fx1 xn, yeah? And this function extends holomorphically to a neighborhood of the box 0, 1, n. Yeah? Because all these exponents are positive. This is in n. So you can use this lemma. And by using this lemma, we obtain that so, 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 + 2 × 1 by using this lemma. This formula star and the lemma imply that for real S big enough, we have the integral S equal E minus E alpha minus S, and we will get the 1 over the product from G from 1 to N of exponential 2pi S alpha G minus 1. And here you have the integral on E epsilon to N, and you have Z eta minus S alpha minus 1, and you have 1 plus sum of beta less than alpha and E beta Z alpha minus beta to power S dz. And as you can see, this is holomorphic function. This is holomorphic in C for epsilon small enough. This is holomorphic, and this formula gives you the analytic continuation because this is also holomorphic, and the poles are given by the zero of these factors. So we obtain that this implies that S eta Ts has homomorphic continuation to C with pole of order at most n, because each factor has sample 0, pole of order less than n, and the set of pole, it's included in the set of 0. It's in the set of so we have this is equal 1, so set G K over alpha G K in N. Okay. So this is not the more useful method, but it's at least if you are interested only by analytic continuation, this gives you analytic continuation for polynomial with dominant monomial, and for general polynomial, if you transform by Sargos theorem, you can construct some modification omega k, which transform your polynomial to polynomial with dominant monomial. So now I will return to this theorem and will explain in more detail how to prove this theorem. So we have the following fundamental lemma. So we say that but before stating the lemma, I need a notation. Let E be a cone given by the formula with vertex alpha in R plus n minus 0, and if you remember, I defined the Newton polyhedron at infinity of polynomial p, and it looked like something, for example, on dimension 2, it looked like this, for example, and we take a vertex, alpha, and the cone it's associated to this vertex, it's this one. Yeah? And it's given by equation of the form E equal to set of beta in Rn such that lambda k beta it's less than 1 for all key equal 1 to n plus p. So in dimension 2 you don't need p, as you can see in this picture. P is equal to, but in dimension 3 and greater than 3, sometimes you need more vector than n vector. And we assume that this minimal, and so P and N, and we have the lambda k are vector in R plus N plus P. So we define S alpha as the set of elements of 1 plus infinity n, where x alpha is dominant. It corresponds to set where the monomial corresponding to this extremal point is dominant. And we have the following lemma. There exists P change of variable of the form omega 0 omega p in the set omega n, such that each omega e is associated to a subfamily lambda e0, lambda e1, lambda en of this family, and of lambda 1 until lambda n plus p, and to the set S alpha, it's equal up to a set of measure 0 to the distant union of the image by omega k of 1 plus infinity n for key from 0 until p. What? What is lambda?
Did you define this before, or it's just defined here?
Lambda I are this vector.
Ah.
The polar vector of the face of the cone.
Polar vector.
Yeah.
So on
For example, in this case, you have lambda 1 here.
This is the normal of the face, or?
Yeah. Lambda 2. This is polar vector. Polar vector associated to the face. In this case, you have only two polar vector, but in a high dimensional case, you can have more. More, but okay, so it's explicit in you can construct them explicitly, and they give you this change of variable, which some sense give you the region. You have what we are doing is that our polynomial. If the polynomial has a dominant monomial, then life it's easy. because you can use this method I explained. So we need to reduce a general case to this case. So it's some idea of resolution of singularity. So we choose domain for any vertex alpha. We need to understand the set when the monomial x alpha is dominant. It's dominant, and what said this lemma is said that the set when alpha is dominant, so it has bad geometric, it can look very bad, but we can transform it by some omega k. It's the image of some, it's the image of this set. And of course, you need it's the union of the image of this set. And in dimension 2, you need only one omega e. So this is what this theorem is saying. You are looking for the region when some monomial is dominant, and he said that even if it's look bad, you have some change of variable, which it is the image by some good transform of this good set. And to be complete, you have this set 1 infinity n. It's the disjoint union of S alpha up to set of measure 0. S alpha when alpha is extremal point, because if p is not extremal point, it cannot be dominant. So it's disjoint union of this. So if you want to study your function here, you have just to decompose the integral on the sum of integral on this set, and in each set you use this transform, and this transform has good property because she transforms your polynomial to polynomial with dominant monomial. Yeah.
Because here you just use a vertex, so zero-dimensional faces. In what you said, you start with a cone attached to a vertex.
Yeah.
So you are just using vertices
of the neutral polynomial.
You don't use other faces. For instance, one-dimensional faces or two-dimensional faces?
Not in analytic continuation here, but it's used, for example, if you want to control the poles. Sometimes you need to understand also what happened for this. For what I am given today, we need just this. But for example, if you want to characterize the first pole, you know that the first you have to take the diagonal and to check the smallest faces meets by the diagonal, and this point give you the first pole, for example. So you need to use also the other faces, but if you need more precision. Okay, so maybe the proof of this lemma is not so hard, but maybe I don't have time to I prepare it, but I will not have time to give it here. And if you are interested by proof of this lemma, for example, you have just to look to the paper of Sargos, for example. Paper of Sargos in Annals of Fourier in 1986 4 or 6. So, and this give you the main idea of the proof. So just to be concrete, for example, if you are to take an example, for example, Px1, x2, something like this, just to dt plus other term. For example, if you are interested for discrete zeta function in quadratic case, you have something like that with d equal 2, which appear. And to study the meromorphic continuation of the integral here, the Newton polyhedron in these cases, it's easy. You have just the point d0 and the point here 0d. And so this is the Newton polyhedron. So you have two vertex, vertex 1 and another vertex here, alpha 2. So you have here, for example, the equation of this phase is x2. It's x1 equal d. So the vector lambda 1 it's equal 1 over d 1 0. This is the vector lambda 1. The vector lambda 2 here, it's the equation here is it's x1 plus x2 equal d. So lambda 2 is 1 over d 1 1 1, and the equation here it's x2 equal d. So the vector lambda 3 it's 1 over d 0 0 1. So we have only two transform. So we have the transform omega 1, which equal lambda 1 omega of lambda 1 lambda 2, and the transform omega 2, which equal omega lambda 2 lambda 3. And omega 1 of 1 infinity 2 give you S alpha 1, the set when the monomial x alpha 1 it's dominant, the set when this is dominant, and the omega 2 of 1 infinity to give you the set alpha S alpha 2 when the set when this monomial is dominant. And we can write explicitly this function omega 1 of x1 x2. So we have the formula. So we have so here we have x1 x mu1 x mu2 and mu1 mu2, so it's equal to x1 mu1 1 x2 mu1 2 x1 mu2 1 x2 mu2 2, and as I explained, the mu eg it's the transpose of the lambda eg. So this is x1 lambda 1 1 x2 lambda 2 1 x1 lambda 1 2 x2 lambda 2 2. So this is the transform x lambda 1 1, it's x1 1 over d, and x2 lambda 2 1 it's 1 over d, and here we have x1 lambda 1 2 it's 0, and lambda 2 2, so x2 1 over d. But sometimes the exponents are not integers. Sometimes it can be a problem, but it is not a real problem. You have just to add another change of variable. The change of variable x1, x1d, and x2, x2d. You take a power of each variable, and then you remove the d. And this is classical blown up. Blow up. So this change of variable are some blow up at infinity in some sense. Just expressed in combinatorial term. And you can compute, so you compute this one, and you can compute in the same manner omega 2, and you know that the 1 infinity 2, it's equal to the union of these two sets, so it's equal to omega 1 of 1 plus infinity 2, union omega 2 of 1 plus infinity 2, union some set of measure 0. So you use this decomposition to compute explicitly your integral and to obtain an explicit meromorphic continuation, and you can also compute with this change of variable the values and other things. So, c'est fini? Non, c'est pas fini. So this method, I like this method because it's really explicit, and if you want to use Aronnaker theorem, if the polynomial is not degenerate, then things are more complicated because you cannot use this Newton polyhedron, but you told me that now with Pierrette you can do it for n equal to. So it's but it's good news. It's good news when you can use Newton polyhedron. It's good news. But in general, for higher degree, it's not possible. So you need to use resolution of singularity, which is not so explicit, and so things are maybe less complicated, more complicated. Now I will explain how to prove analytic continuation for integrals for series, because this is the result. Now it's about integrals. So for series, we use usually what we call integral representation formula. So integral representation formula, it's something which maybe how to connect the series to some integrals. So I will explain, for example, for the general case, the series it's look like a discrete sum, and this sum it's here sum 1 over Pm s, and you are looking for integers. For integers, but what is integers? Integers are solution of the equation sine pzg equal 0. So you are looking, you are summing something yes, over sum of m such that sine of pzg equals 0 for all g. So it's not standard, but
you have negative roots.
But you have with equality is a g positive. Okay. just to give an idea. So usually you need to understand it. So the idea is to find some formula which give you sum of function when alpha is running in some open set U, and alpha is solution of some equation with, so set U F, it's the set of Z in U such that F1 of Z1 of Z equal Fn of Z equal 0. So you have some function F1 defined in U, holomorphic in U, and so if F1 are and Fn the hypersurface intersect properly, then this set is finite. So you are counting the points of this set, and you are trying to sum some function until the point of this set.
You mean this set is finite?
What?
You mean this set is finite?
Under some assumption on F1, Fn, yeah. And for good function, we have this, it's finite, and we need to construct some good representation formula, represent this kind of sum by integrals. So a lot of work has been done in multiple complex variable and complex geometry in this subject, and there are a lot of work. I don't have time to explain all of this in detail, but I can give you a formula which I like very much, and it's useful. And this is essentially a reformulation of Buchner-Martinelli formula. Okay, but you can find this result in the book of Iger and all, Bernstein and etc. And in this book, they obtain this theorem, which is a consequence of Buchner-Martinelli formula. And this formula, this theorem said that let U be an open an open bounded domain of Cn with not necessarily smooth, but piecewise smooth boundary let F1 Fn be an holomorphic function in a neighborhood of the closure of U. Let G1, Gn be not necessarily holomorphic, be C1 function in a neighborhood of the boundary of U. Assume that for all Z in the boundary of U, we have the scalar product Gz Fz. So G we denote by F the function F1 Fn, and we denote by G the function G1 Gn, and we assume that this sum it's non-vanishing for in the boundary point. Then the set Z UF defined as the set of points Z in U when all these functions vanish is finite, is a finite set. And for any function h from u, the closer of u to c, which is continuous on u, on the closer of u and holomorphic in u, we have the following formula. I will write it in this part. We have the following formula. The sum for alpha and z uf of h of alpha can be represented by this integral. I have here some standard constant. I don't want to give it, but it's look like 1 over 2 p en n factorial, something like that. So this is not important as a constant, but it's explicit constant. The integral on the boundary of u h z, and here you have the differential form, some key from 1 to n, minus 1 to key minus 1, g key of z, and here you have d g1 until dgk until dgn. So you forget only this factor, you omit this factor, and here you have df1 until dfn divided by gz scalar fz to n. So it's quite general formula. You have to choose your function f. If you are interested by integral point, for example, you choose fgz equals sine. If you are interested by integral point, then you choose fgz equals sine of p zg, for example. But if you can use it for other points, not necessarily if you are interested for point of another lattice than Zn, you choose other function, etc. And it gives you, what is important in this formula, that you have an integral on all the boundary. All the boundary. In some sense, this is the right generalization of residue formula. Because you know, for residue formula in the one variable case, you write your function as the integral on some cycle around z of ft or t minus z. Yeah? And if you want to extend, you can extend this naively to the several variable case. For example, by writing fz1 Zn equal 1 over 2p en, the integral of the product of cycle Zn ft1 tn t1 minus z1 tn minus z1 zn tz1. So this is also an integral representation formula, but it's not a good formula because you are integrating in the product of cycle, and the difference with this that you have your domain U and you are integrating in the boundary, like in the one curve. Here you are integrating on the boundary of your domain. Here also you are integrating on the boundary of your domain. So this is something. This is the right generalization of this formula. So this is not. In some sense, this is not so useful. What? Yeah, but it's not so easy it's products of some cycle, so it's not. You have your domain. You have your domain. You need to integrate on the boundary of your domain. This is the idea, but here it's not so useful for this kind of problems. Yeah. Because you separate the variable artificially. And here you have no artificial separation of the variables. So for people interested by this formula, for example, for Buchner, this is a consequence of Buchner-Martinelli formula. A good reference, it's Heineken books, Literaire Heineken, I don't know if you know these books, for Buchner-Martinelli formula. And you can also consult the book of Alain Iger and Bernstein when the proof of this formula is given. If you, yeah, because each equal 1 can be used with. And in general, we use this formula in for you are interested in some point, you are summing in general for an infinite number of you are summing on point on some lattice, for example. Then what we apply, you chase your domain U, which depend on some parameter n, and when n tend to infinity, the domain recover all all your points. Okay, so but for today, so I start. We work with no degenerate polynomial, so it's not necessary to use this formula. This formula can you if it's useful for if you are not in the non-degenerate case, and if you are working, for example, if, you are counting the point on semi-algebraic set, and then this formula is really useful, and I use it, for example, in my paper in composition to obtain meromorphic continuation. I don't know another way to do it without using this formula, and but in the case we are working with today, the situation it's some more sample. So we have just to prove this the theorem so ZPS or sum of 1 over PMS has homomorphic continuation, so converge absolutely in sigma bigger than sigma A, and has homomorphic continuation. Morphic continuation to C with pole of order less than n, and the set of pole P, it's in some sequence of this form, and has meromorphic continuation with modulus growth. So I will complete the proof in the case of today. So today we work with polynomial of positive coefficient. So in this case, this theorem it's a result of also of Sargos. And in this case, the situation it's something more simple. So to prove this theorem, we have just to represent this series by by the integral, and for the integral we have the result. We prove the result, and to prove this result we have just to use this formula. So for take the real axis, so here you have 0, here you have 1, 2, etc. We'll take here 1 over 2. Here we have integral point, and we will consider this path. So here we have the angle theta minus theta, and we consider this path. Here we have, so come from here and you go here. So this is minus gamma theta plus, and this is gamma theta minus. We consider this path for theta from between 0 and p over 2. And by using this path, it's easy to see that the integral from if f is a holomorphic function in a neighborhood of gamma theta, it's this set. And satisfy this growth condition for z in gamma theta. Then by residue theorem, it's easy to see that the sum from n from 1 to infinity of fn, it's equal to the integral on gamma theta of fz and exponential 2p ez minus 1 dz. And this is equal to the integral of on gamma theta plus f to the fz divided by 1 minus exponential 2p ez plus the integral on exponential 2p ez minus 1. Just elementary computation. And from this, you deduce that sum from n to infinity of fn, it's equal to, have just to write this as the integral from on gamma theta plus of fz dz plus the integral on gamma theta plus on fz exponential 2p ez over 1 2p ez plus the integral on gamma theta minus fz over 1 minus exponential 2p minus exponential minus 2p ez, and here minus also. So we have this formula, and this integral by residue theorem, it's the same as the integral, it's equal to the integral from 1 over 2 to infinity. So this is equal to the integral from 1 over 2 to infinity of fx dx plus the integral on gamma theta plus fz exponential 2p ez divided by this dz plus the integral on gamma theta minus fz exponential 2p minus 2p ez over 1 minus 2p ez dz. So you obtain this formula, and you have just to iterate this formula. So if you iterate this formula, you obtain okay, so if you iterate this formula, you obtain the following formula for several variable function. You obtain that the sum of this form then 1, it's equal to sum of, you integrate on gamma theta plus n1 times, and you integrate on gamma theta minus n2 time, and the last integral is on 1 over 2 plus infinity n, and you have f z1 until zn1, zn1 plus 1 until zn1 plus n2, and the last are xn1 plus n2 plus 1 until xn, dx1, dxn. And this is true for function f. You assume that there exists theta in 0 p over 2, such that f z1, zn is holomorphic in a neighborhood of gamma theta power n, and satisfy f z1 zn less than the product z1, the module to power minus 1 minus delta for some positive delta. Yeah, so for function, holomorphic function in neighborhood of this set, satisfying this condition, by iterating the one variable case, you obtain this formula. So you can apply this formula to f equal p minus s. And for s big enough, these functions satisfy this assumption. So if you apply this with f equal p minus s, so here I forget the factor product of exponential plus minus 2p z over 1 minus exponential plus minus 2p z. And if you apply this, you get your zeta function. And as you can verify by hand, this function decreases in an exponential way. So you can, which means that for analytic continuum, you can forget this part. You can treat this term as a parameter, and this. So you have just to understand the integral, the analytic continuation of this part, and if you use the last theorem, you have the result. So you fix this parameter. So if you fix parameter z1 until zn1 plus n2, you have a polynomial which depends on this parameter, but a polynomial on these variables, real variables. And you integrate on 1 over 2 plus n2, n minus n1 minus n2. So you can apply the last theorem on integrals. And this theorem give the analytic continuation, meromorphic continuation. And by using, in addition, the fact that this kernel decreases in exponential way at infinity, so it is enough. You conclude. So in the case of polynomial with positive coefficient, the situation it's in some sense easy to understood by using Newton polyhedron, and this is enough in some sense for kind of the Dirichlet series coming from number theory. Of course, if on singularity theory, it's interesting to work with polynomials which are degenerate. But for Dedekind zeta function, etc., the polynomials which appear are elliptic. So the singularity are not so worse, so this is enough. But some other problem coming from number theory, but not in this way. Forced sometimes to study zeta function with polynomials which are degenerate. So maybe I will stop here today.
C'est la formule d'Abel-Plana en fait que tu fais.
La formule 2
Abel-Plana.
Enfin, je ne sais pas comment il s'appelle, mais c'est une formule classique. Donc c'est une formule classique. Bon, Sargos l'avait utilisé, d'autres personnes, mais je sais pas qui est le premier qui l'avait utilisé.
C'est Abel.
Oui, c'est une formule. À une variable, c'est une formule qui est très ancienne. Donc c'est une formule qui est très très ancienne et qui suffit dans le canon dégénéré. Donc il ne faut pas s'en priver.